All right, so we left off yesterday and we had just kind of gotten near the end of talking about what was going to be on the biology part of the final exam, okay? And I just talked about multicellularity, okay, and specialization. Parts, the layers of the leaf were going to be important because that was our example of specialization in cells of a multicellular organism. So make sure that you go over those, okay? Remember that specialization means that some cells have a certain job and other cells have a different job, okay? And that they have different structures in order to be able to do that. Maybe different amounts of a certain organelle, okay, or just different shapes or different abilities, like the guard cells can make the stomate open and close, right? Whereas the spongy layer cells are kind of, they don't really have a shape, but they make air spaces between them and things like that, okay? Remember also that the cell transport processes are important not just for cells, okay, but also for the plant, okay, because osmosis was used to help transport water up the plant. Tropisms and plant growth patterns are also going to be important. Okay, plant growth and development. So know the hormones that a plant uses, okay, and how they help with tropisms, if they do help with tropisms. Just keep that kind of stuff in mind. There could be questions about that as well, maybe in the multiple choice. In fact, in the multiple choice, there's a lot of questions about plant growth and development. And those are going to also have pictures, right? There's quite a few pictures in both parts of your final exam, right? So the visual aids to kind of help you with the question. All right, now that ought to do it for biology. Okay. Pardon me? Geotropism, that's gravity. Phototropism for light. Thigmotropism for touch. Most of the time, I will pick a situation where it's just one, where one is definitively more than the others. Yeah, thigmotropism. All right, for physics. Well, because we did most of the bio yesterday. Right. Okay, so for physics, the big thing, or sorry, that we started with, right, was the types of energy. Okay, and in types of energy, we talked about, like, the chemical energy, electrical energy, solar energy, all that kind of stuff. There could be some multiple choice questions about that, but it's not something that you need to review heavily because it's kind of common sense stuff. You do need to know the laws of thermodynamics. Okay, so first law of thermodynamics is really just the law of conservation of energy. And the second law of thermodynamics tells us which way energy flows, okay, from hot to cold or from high to low. Right? There could be opportunity for you to apply those in answering a question on the exam, okay, possibly even in the last unit. Okay, in the global systems unit, we talked about the laws of thermodynamics, especially the second law, several times. So you could probably work it into an answer in that unit as well. Okay, you need to know the types of systems. There could be a multiple choice item about the three kinds of systems: open, closed, and isolated. Okay, just make sure you remember what they are. All right, and that's, I mean, really what you need to get out of kind of those first two lessons. Okay. From there, we talked about scalar and vector quantities. Okay. Scalar quantities that we talked about were things like distance, speed, time, work, and energy. Okay? All of those things are scalar. That is, they do not require a vector on their answer. Right? And also specifically, when we first started talking about this, our first scalar formula was speed equals distance over time. Okay? Is it possible you could have a V equals D over T question on the final exam? In the written response or the multiple choice? Multiple choice, way too easy, okay, for like a 4 or 5 mark written response item on a final exam, but it could be a simple one in multiple choice. Okay, and then for our vector quantities, all right, that was going to be displacement, right? Final position minus initial position, velocity, and that was displacement over time, acceleration, and we only talked about it briefly, and it won't be on the final, but force was also a vector quantity. Okay? The only place where force would be part of a work energy theorem question, right? All right, so definitely expect that there could be some multiple choice items about scalar and vector quantities, but more important than that, you need to know which ones are scalar and vector if you're doing a written response item and it says calculate the overall displacement of the object in question 4, and you need to remember that you calculate that differently than distance and that the answer needs a vector on it at the end. Okay, that's really the reason you need to know which ones are scalar and vector, not just to memorize them and get a multiple choice question right, but because you do solve for them differently. Okay, so make sure you know which ones are which. Okay, and then we went to graphing. How important is graphing? Very important. Okay, graphing is a very basic scientific skill. Right, you're going to use it in every branch of science that you go into. Okay, you make graphs in biology, you make graphs in chemistry, you make graphs in physics. Okay, so being able to read and interpret a graph is important. The two kinds of graphs most important for you guys are position versus time and velocity versus time. I would expect you will see both on the final exam. Okay, not necessarily both in the written, okay, but probably we'll see both. All right, on a position versus time graph, remember that the things we can get from a position versus time graph are displacement. Okay, we can find displacement because displacement is final position minus initial position, and a position versus time graph shows us position. Okay, we can also get, so let's just go, okay, so you can get displacement from that and you can get velocity from that. Okay, you can get velocity in two ways from a position versus time graph. If your position versus time graph looks like this, and it's got a bunch of different sections, okay, then you would probably have to go v equals d over t in order to get the velocity because you don't have a single line. If you have a single line, then you could calculate velocity by calculating the slope of the line. Okay, is it reasonable to expect you're going to be asked to do one of these types of calculations? Yep. Okay, y equals mx plus b is definitely going to be something you'll have to do on the final exam, whether it's on a position versus time or a velocity versus time graph, maybe both, okay, but you're definitely going to have to use y equals mx plus b. All right, that's what we can get from the position versus time graph. There could also be a question that just simply asks, on this graph, explain what's happening in the 4 sections, right? So in this section here, this first section, the object is doing what? If this is a position versus time graph. Moving forwards at a constant velocity, and now it's moving backwards at a constant velocity and so on. What if I had a graph that was shaped like this? Then it's accelerating. Just things like that that shows you can interpret what's happening on the graph. There could be a question like that as well, right? In multiple choice or written form, right? But being able to read the graph is important. All right, for velocity versus time, right? We can calculate displacement from that graph. Right, that's the one where we have to use average velocity times time, but it ended up working out that it was like the area, okay, of the shapes. Okay, so make sure you remember that that's how we do that. And we can also calculate acceleration. Okay, how do I get acceleration from a velocity versus time graph? Okay, it's meters per second squared. How do I get it? No, that's how I get displacement, because that's base times height. Okay, so if I've got a, here's my velocity versus time graph. It's doing that. That's an accelerating object. Okay, that's one of the ways I could use the formula, Vf minus Vi over T. I could do that, but that formula came from what formula? Slope. Okay, if I do this, that's the same as saying m equals y minus b over x, because this is meters per second and this is seconds. Y is Vf, b is Vi, x is t. Okay, so it depends on what kind of a graph you have. Right? If you have a graph like this, you'd get that equation. You'd get y equals mx plus b on it. Right? And that's what I'll do. If you get a graph that's just one line, the equation will be there. Use it. If it's a graph that has lots of different parts, okay, then obviously you can't. Okay, then you have to use the a equals Vf minus Vi over t and get the average acceleration over the whole trip instead. On a velocity versus time graph, m is acceleration, yes. No, on a position versus time graph, what is it? It's velocity, okay? Because on this graph, okay, if I have a graph that looks like this and it's a position versus time graph, so meters and seconds, when I manipulate this, m equals, okay, y minus b over x, but that's actually final position, because this would be a position minus initial position over time. That's displacement over time. Yeah, that's where we get that formula from as well. Right. Most of the formulas we use are in some way derived from graphing. All right, is that ringing a bell for everybody? Okay, so probably some decent marks to be had in that section of the test. All right, then we have acceleration. Okay, we need to know what acceleration is and probably be able to use the formula. Okay, it might just be multiple choice, okay, like because it's a fairly simple calculation, but expect that you're going to have to do one. Okay, so that is using a equals Vf minus Vi over T. Okay, and then we'll solve for some part of that formula. Okay, from acceleration, we then went to what I told you was what I thought is the most important concept in all of high school physics. Okay, work energy theorem. You're definitely going to see at least one work energy theorem problem on your final exam. Okay, so what do we need to remember about the work energy theorem? That work is a change in energy, and that can also be calculated by multiplying force times distance. All right, so if I have, let's say like a toy car on the floor and it's just sitting there, it has no mechanical energy. It has no potential because it's on the floor, and it has no kinetic because it's not moving. If I kick it, okay, then I'm going to be exerting a force on it through a distance, and I'm going to change its energy. Which kind? Probably it's kinetic. I'd make it go faster, right? So then I would set it up like this. I would say, all right, force times distance equals, okay, the change in kinetic energy, which means I could also say that force times distance equals 1/2 mvf squared, final kinetic energy, minus 1/2 mvi squared, the initial kinetic energy. Right? And then I'd be asked to solve for either one of the speeds or the force used or the distance over which the force acted, depending on what I was given in the question. Right? Did we do a lot of those? Yes. Okay. So there's a lot of those that you can watch in a podcast or look at. You've got lots of ones on worksheets with the answers there. Okay. To check and see if you know and know and remember how to do them. Right. When the initial velocity is 0, then the initial kinetic energy is 0 because you'd be multiplying that term by 0. Yeah, you could just cross that out. Yeah. I mean, you could leave it in there and plug in 0, but like, what's the point, right? You're subtracting 0. It doesn't change anything. Oh, EP would be m times g times h, right? Yep. Well, the MGHF minus MGHI isn't there. That's something you have to know, that delta means final minus initial. but MGH is on there. Okay, I showed you guys the data sheet you're getting, right? Yeah. Okay. All right. Any other questions with work energy theorem? Right, so definitely expect you're going to get one that's either a change in potential or a change in kinetic. It's one or the other. It's not going to be both. Okay, when you get to physics 20, we'll do ones that have both.
If it's a different the acceleration question, and it says it's falling off a roof, and it doesn't give us acceleration directly.
Yes, anytime something is falling on Earth, A is 9.81. Yeah, always.
When do we have to cancel out all the M's?
That's in a conservation. That's what I'm doing next. All right, so next thing, conservation of mechanical energy. All right, so in a conservation of mechanical energy question, our initial energy equals our final mechanical energy, right? And what two forms of energy add up to get mechanical? Potential and kinetic. All right, so that means that we have EPI plus EKI equals EPF plus EKF. And then we expand that further to include the formulas M times G times H initial plus 1/2 M times V initial squared equals M times G times H final plus 1/2 times mass times V final squared. Okay, now as Jacob had mentioned here earlier, what's the kind that you can cancel the mass off on? This one, right? Mass is in every term. As long as I'm not being asked to calculate one of the forms of energy, if I'm asked to calculate kinetic energy final, then I have to use all the M's. Okay, but we've never done one like that. So you're going to be asked to calculate height or speed, one or the other. Okay, you can cancel off the masses. Will I give you the mass in the question anyway? Yes, I will, okay? But it doesn't matter. You can plug it in if you want to. It's just more numbers to plug in your calculator, all right? So we would just isolate whatever thing it was we didn't have, okay? It's like roller coaster or sled going down a hill were some of the examples that we did in class. All right, Ken. Yes, like, okay, let's just say we wanted to solve for HF right now. Okay, so I want to solve for HF. I cancel off all my M's, and then I would subtract 1/2 times VF squared over to the other side, right? So I would have G times HI plus 1/2 VI squared minus 1/2 VF squared equals G times HF. And then what would I do with G? Divide it over to the other side. Okay, now HF is by itself, and I can solve for it, right? If you're solving for VF, then it's the same idea. You divide the half over, and then you have to square root because VF is squared. Okay, ringing a bell? You guys were pretty good at those. So, okay, there's definitely going to be one of those on there. All right, and that tends to be kind of a big mark kind of question because there's a lot of steps. So make sure you show all your work. In fact, make sure you show all your work for every problem that you solve. Mole equation, V equals D over T, graphing, show your work, right? There is nothing worse than for me to look at an exam and see just a number, know that that was what the person thought the answer was, and know that it's wrong. And since it's the only thing that's there, what can I give you? Nothing. I can't give you anything. All you have is a number that's not right. If you showed me how you arrived at that number, I can probably give you something. And usually, guys, when someone does that, they've done everything right except punch it into their calculator. Okay, they made some kind of simple mistake. They accidentally, their fingers got clumsy and they hit two numbers when they thought they only hit one and didn't notice. They knew how to do the question and should have got 5 out of 6. But because they showed me nothing, they got 0. Okay, I can't mark a question and say, I know this kid. I know they knew how to do it. I'm going to give them 5 out of 6 anyway. I'll get fired. Okay, like I can't do that. You have to show me that you know it. Okay, so show your work when you're doing this. Okay.
What's the question where the answer has to have like downhill?
If it's a vector quantity, so if it asks, if it was saying something's rolling down a hill, what's the final velocity? Then you would have to say down the hill, right? If it said what's the final speed, doesn't matter. Generally, we say no. If you want some, we can provide you with some in the exam writing area. But if you're gonna write it on the scrap paper, it's probably worth writing on the exam, especially if it's work to do with solving something. Put it on there. Okay. All right. Any other questions to do with conservation of energy? All right. And then after that, we talked about efficiency. Okay, and that's just going to be multiple choice stuff. Is the work out divided by energy in, right? Energy in is always going to be the bigger number, and the work that gets done is always going to be the smaller number. And then yeah, we said times 100, but we said we'd always do that just in our head, right? Okay, I think that covers everything that's in the physics section.
What about the names like the scientists?
Okay, I mean, if you want to read that lesson over and just review it, do it once. Don't spend a lot of time making recipe card notes about who Volta was and that can who Joule. Well, Joule, he was kind of important because he got the units named after him, but no. If there's one, it would be one you would know. Yeah. Okay. I said that yesterday. Yeah, I'm not concerned with names and dates and things like that. Like there's some that you'll remember because we went over them so many times. But okay, like I'm not worried about every nitty gritty detail. Like what year did the neutron get discovered? Like I'm not going to ask that. No, a perpetual motion machine can't do any work. An isolated system, okay, is not going to lose energy to its surroundings. So it's more about thermal energy, right? I mean, it could also be about mechanical. If you isolate something, then yeah, it can do work within the system itself, transfer to different parts of the system, but not to the surroundings, right? So it's not going to do any work on the surroundings. It could be doing work on different parts of the system. There really isn't one. Yeah, it's essentially impossible to completely isolate something, right? There's always going to be energy lost, work done against non-conservative forces. There's just no way to avoid doing that, right? Now, most of the stuff we do is supposedly happening in isolated systems, right? Like the law of conservation of energy questions, all those roller coasters are perfect and they lose no energy to anything, which is just makes life easier for us. But yeah, you know what? That's a good question. I do believe I did put a multiple choice question or two about variables, and yeah, here's an experiment. Tell me what the manipulated variable is or the responding variable. Yeah, so you should probably just go over that. I mean, you guys kind of know that because we've done a lot of labs. So, okay. Trying to think if there's anything I missed here, guys. Not that I can think of right now. Okay. Couple of things for you here. Okay, you guys write in the afternoon, so make sure you get a good night's sleep. Okay, like these are simple things, but they're important. Okay, like people really discount the value of a good night's sleep before the exam. Okay, a good breakfast and a good lunch that day. Okay, that doesn't hurt either. Okay, a fed brain works better than a starving brain. All right, so make sure you get some good food and stuff in you during the day. Make sure that you before the exam, because I see people doing this and I laugh in a sad way every time I see it. There's people sitting outside the door to the exam and they're just going over their notes and they're like just freaking out. You could cut the tension with a knife, kind of thing. Okay, don't do that. Right, half hour before the test, stop. Right. There is nothing you can put into your brain in that last half hour that you are going to retain. There's nothing that you can do in that last half hour that will help you because your short-term memory will not keep it long enough for it to help you. Okay? And this is what happens to a lot of people who do that. They're cramming, they're trying to put all that stuff in the last 5 seconds before. Okay, they get into the exam, they're not allowed to start writing for like another 10 minutes. They're sitting at their desk. Then we say, all right, you can start. They open up the test and blank. Because that's how long your short-term memory lasts. just long enough to give you that sensation of I open up the test and I can't remember anything. And that sucks. Okay, it's just creates this feeling of panic, and that's not the way you want to start your test. Okay, so don't try to put a bunch of stuff into your head right before the test, because that will happen. Okay, that's just the way your brain works. Your short-term memory only lasts for a short while. Okay, you're not going to commit anything to long-term memory in the last 30 minutes before the test. So don't try. Okay, you do your preparing before, right? Do your preparing in the days before. Okay, hopefully the weeks before, but that's kind of past now. Now it's the days before. Okay, but get it done before that day. Okay, you come in and you just write the test. All right, and if you want to study in the morning, how many of you have a test in the morning that day? Okay, so a few of you. All right, so on the Wednesday, yeah, the 24th. Okay, if you have a test in the morning, okay, write that test, and then, like I say, absolutely do not pick up your science stuff. Don't look at it after that test. Okay, your brain has just done a lot of work. It needs a break. Okay, go get something to eat. Take a little nap. Okay, something like that. Let your brain rest and recover before you write the next test. Okay, that's going to be better for you than any amount of studying you could do in that small space in between. Right? In order to help with that, I am not available for help in between that morning test and the afternoon test. I am not going to facilitate your panic. Okay, so don't come find me. I'm hiding. Okay, and I'm doing that to help you. Okay, because I don't want you trying to do that like last second cramming that I know isn't going to help you. All right, so you're going to be ready. Okay, you guys know your stuff, do your studying, you're going to be fine. Okay, everybody with me there? What things do we need to bring to the final exam? Calculator with fresh batteries or extra batteries. Okay, clothes. Good idea. Good idea. You might get taken away if you show up naked to the test. That would be bad. Okay. And by clothes we mean adhere to the dress code. Showing up in a Speedo, also not cool. Okay, don't do that either, especially in January, because you probably get frostbite on something you wouldn't want to. Okay. Other things to bring to the test: pencils, a couple of them. Okay, bring a couple of pencils, couple of pens. Okay, eraser. And then if you need, a drink or a snack, bring that too. Okay, just don't bring big stuff with you. Don't bring your bag, not your purse, not your jacket. Okay, leave all that stuff in your locker. Just come to the test with what you need to write. Okay, everybody follow. Don't bring your cell phone. Don't bring your cell phone, please. Your cell phones? No. Put them in your locker where they're secure. Okay. The other place you can put them, like they always say, is in an administrator's office, but it's more secure in your locker than it is there. Okay. That's not because the principals are going to steal your phone. The principals are not going to steal your phone. Okay. But you just never know who walks in there before you get back in there, right? We generally want you to not go in there. I mean, that's the ones we use for the bathroom, right, in the gym. So it's better if you use your main locker as opposed to that one. Besides, you don't have phys ed probably second semester, right? You're an exception, but okay. Yeah, so you're going to be asked to clean out your phys ed locker anyway before exams. So that won't be an option for most of you, okay? Any other questions there? All right. Any questions you want me to answer or go over? Okay. How many moles of, let's say, sodium oxide are in 25 grams? All right, so that would be the first and easiest of the mole equation types. Okay, in this question I am given the mass, so that's little m, 25 grams. I'm also told the material is sodium oxide, so that's Na with O. It's an ionic compound that needs to be dropped and swapped, so it's Na2O. Very important we get that right. If we don't get that right, we won't get anything else right. All right, so that'll help me calculate the molar mass. So that'll be 22.99 times 2, because there are 2 sodiums, plus 16. Okay, and that'll get me my molar mass. Oh, 22.99 times 2 plus 16. All right, 61.98 grams per mole. All right, so I have little m and I have big M. The mole equation formula is little m over big M, so I don't need to manipulate. N is going to equal 25 divided by 61.98, so I'm going to have less than a mole here. All right, so I have 0.40 moles. Okay, everybody all right with them? Jake?
We go over like stuff.
Sorry, he wanted me to go over all 4. All right, second one. What is the mass of 7.2 moles of magnesium iodide? All right, so in this question they gave me N, 7.2 moles. And they gave me the formula. It's magnesium iodide. This is a +2, that's a -1, so we're looking at MgI2. All right, so we've got 24.31 and 126.9. Okay, so calculate our molar mass. Okay, so 278.11 grams per mole. All right, so I have N and I have big M. So N equals little m over big M. I'm trying to find little m. What do I do with big M? Okay, multiply both sides by it, right? So there's my formula. So that'll be 278.11 times 7.2 moles, and that'll give us our mass. Whoop. 278.11 times 7.2. Okay, so 2002.39 grams would be my answer there. All right, so those are the 2 kind of simplest ones. They don't involve using Avogadro's number. The other 2 involve using Avogadro's number. Okay, how many molecules of potassium nitride are in 75 grams? Okay, so we're looking for the number of molecules. Okay, that's something we don't have. We know the mass is 75 grams. We know the material is potassium nitride. This is a -3, that's a +1. So we're looking at K3N. Okay, so we're looking at 39.10 times 3 plus 14.01. Okay, so 131.31 grams per mole. Okay, what can I find with little m and big M? Number of moles. All right, let's find that first. Okay, so N equals little m over big M, so that'll be 75 grams divided by 131.31. All right, so I've got 0.57 moles. I'm going to keep all those decimals, though. I'm just going to write the 0.57 here for now. All right, I know the number of moles, and I'm looking for the number of molecules. I need to use Avogadro's number. Am I multiplying by it or dividing by it? Multiplying by it. Okay, is number of molecules going to be a big number, right? If I want a number to be big, I usually multiply. Okay, if you want like kind of simple logic on that, right? So to get the number of molecules, I take the number of moles and I multiply by Avogadro's number, because Avogadro's number is the number of molecules in 1 mole. All right, so I take my 0.57 and I multiply it by 6.02 times 10 to the 23, and that'll give me my number of molecules. Okay, so 3.44 times 10 to the 23. Molecules. Well, your calculator will spit it out that way. Yeah, it won't make a number that big. Yes. Yeah, this would not be. I mean, this is 5 marks. I wouldn't make it that worth 1 on a multiple choice. That's what the diploma exam is for. Making questions worth lots of work worth 1 mark.
Are there going to be any questions that you want us to convert in these questions?
These ones. But your calculator is going to spit them out that way anyway. I can't think of another one where that would be all that important. Okay. Any calculator should be able to do that. Yeah, you just hit the EE button. Yeah. On here, I just use the answer function. Okay, like if I see how I calculated the 0.57 here, then I just went second and I hit down here on the negative. See where it says ANS? That stands for answer. So that just plugs the answer from the previous calculation in. Okay. Yeah. Well, no, but I mean, once you get working, you can save the numbers back into the memory. We're deleting anything you have on there before. All right, and then one last type. And this is one we did yesterday. I did one like this yesterday when we did the review. What is the mass of 7.5 times 10 to the 26 molecules of hydrogen chloride? Okay, so we know the number of molecules. 7.5 times 10 to the 26. No, N is moles. Okay, so number of molecules is 7.5 times 10 to the 26, and okay, the molar mass of hydrogen chloride, HCl, is going to be 1.01 plus 35.45, or sorry, 35.45. Okay, so that's going to mean 36.46 grams per mole. All right, everybody with me so far? All right, what does Avogadro's number tell me? Number in 1 mole. So the number of moles is going to be a small number or big number? Small number. So do I want to multiply by Avogadro? Like, do I want to take this big number here and multiply it, or do I want to divide it? Divide it, then I'll get a nice small number. All right, so N is going to equal the number of molecules divided by Av's number. Okay, so that's going to be 7.5 times 10 to the 26 divided by 6.02 times 10 to the 23. All right, so it's a lot of moles. 1,245 moles. It's a lot. Okay, so now that we know the number of moles, and again, I'm going to keep all those decimals. Right now, I'm just only writing that many. Okay, now I have N and I have big M. Can I find little m? Okay, so N equals little m over big M. So I'm going to multiply both sides by big M. That'll give me M. So that'll be 1,245.8 and all the other decimals times 36.46 grams per mole. All right, so I'm just going to take that number, go multiply, and I'm using it. Okay, 36.46. All right, so I have 45 kilograms of hydrochloric acid. That seems like something I wouldn't be allowed to carry around. No, I would. You could just leave it like that. You don't have to convert. Okay, so 45,423.59 grams of hydrochloric acid. Yep. All right, Strachan, you wanted me to do something with wind. What do you want me to talk about?
No, yeah, that's
Oh, okay.
wind stuff. I don't get like convection in that like whole diagram.
That whole diagram. Okay.
Flow and then like the Coriolis
Okay. Here's what you need to understand about this diagram. Okay. The equator gets more of the sunlight, so the equator is warmer. So air at the equator rises. Okay. Now, if it just rose and nothing moved in to replace it, it would create a vacuum. That's not what we want, right? So air moves in from up here to replace it. Okay, that creates a convection current. So air starts to move like this. Because this air that's moving northwards is aloft and then starts to descend because this air is moving out, okay, it's going to wedge underneath and move northwards along the surface. Okay, there's also going to be some cooler air that it's gotten wedged underneath that is also moving northwards. Okay, so there's not like a true convection current at this latitude, right? So in this, these are our kind of three areas here, right? So in this part here, the winds are moving from north to south, right? So we've got essentially warm air that's trying to do this. With me on that, okay? Other warm air at this latitude is moving northward. So we've got this general trend of the second law of thermodynamics holding true. Warm air is moving north, okay? It's moving to the area where it's colder. That's convection. That's the first part of it, okay? The Earth, meanwhile, is rotating in this direction. Okay, so we've got air moving this way and us moving through it while it's trying to do that. When we have two vectors happening at the same time, okay, we draw them tail to head. Okay, and so as a result, what I get is that because this air is moving down and I'm moving into it, it feels like it's doing that instead. Okay, it's trying to move from north to south, but because I'm rushing through it, it feels like it's coming into my face a little bit. Follow me there? Like when you stick your head out the window, right? It's not necessarily windy, but you're rushing through the air at a high rate of speed. Right? So that's what I feel here. It's not really that it's coming from that direction, but because we're moving through it, it kind of feels that way.
air moves north. How does like air move in the southern hemisphere?
Oh, this is just the northern hemisphere. Exactly the same thing happens on the southern half, just in the other direction. Yeah, we're just, hemisphere snobs.
Wait, why does the air feel like it's coming from like the east? Why does it come from the west?
No, at our latitude, it's going the other way. Yeah, okay. So here, because it's moving upwards, it gets deflected this way. Okay, that's why we get westerlies. And then at the pole, it's trying to move downwards again. So anytime the air is moving from north to south, it gets deflected like this. Anytime it's moving from south to north, it gets deflected the other way. Okay, that's all you have to remember. Just say that it's convection in conjunction with the Coriolis effect. That's what makes the winds feel like they're going from a different direction. That's all you need to know. Okay. No, the Coriolis effect.
Coriolis effect is when the
Right. Deflected. Yes.
So is the wind actually getting deflected, or do we just think it?
It's actually getting deflected.
Then why does the definition say the apparent deflection?
Apparent. I mean, if the Earth wasn't spinning, then you wouldn't feel it. So whether it's apparent or not, it's the way we perceive it. Okay? It's just that's the way it's happening. All right? It has to be working because sailing ships for hundreds of years use these winds to blow this way. Right? All right? Hannah. No, I mean, there's movement of air, which is convection, but it's not like a single Hadley cell kind of thing like it is here. No, there's also one at the pole. Yeah. It's the same thing. Just flip this over. Okay. And it works exactly the same way in the south. You guys are really overthinking that concept. This is the last time you'll ever hear that concept in high school science. Coriolis effect and convection combine to create patterns of prevailing winds. That's all you have to know.
What's the hardest unit?
It wasn't the hardest unit. You guys just felt like it was.